This video is sponsored by boot.dev. I like things that go boom, and if you click this video, you probably do too. But unfortunately, not everyone does, and according to my homeowners association, local police, the ATF, the EOD guy, a county judge, a federal judge, my wife, my mother, my cellmate, and my parole officer, you can't just go around blowing things up within a residential neighborhood. Now, I thought this was America, but apparently I'm living in a country that's more like North Korea or the UK. Fortunately, small chemical fireworks, can be substituted with electricity for a number of scientific applications, specifically with an exploding wire circuit. This type of circuit is used for things like plasma research, flash lamps, EMPs, and most notably for the initiation of nuclear weapons. To the casual observer, this may look no different than a hot wire, but an exploding wire actually has a different mechanism of action. As you probably recall from Looney Tunes, to initiate a blast, a humanoid coyote pushes down the plunger on a blasting machine which sets off dynamite, and then hilarity ensues. What's happening here is that the plunger pushes on a rat gear which turns a series of gears that get a generator momentarily spinning fast enough to generate enough current to heat a wire inside a blasting cap that kicks off the whole process. Now, the hot wire by itself wouldn't be sufficient to set off the dynamite. It requires an initiator known as a blasting cap. The blasting cap is a small metal shell filled with an extremely sensitive substance called a primary explosive in very small quantities, like 500 to 1,000 milligrams. These primaries are sensitive enough that they will detonate from the action of a hot wire, but that also makes them extremely dangerous to handle. A little too much heat, a little too far of a drop, some stray static electricity, or even just looking at them funny can cause them to go off. In addition to the volatility, primaries are just plain nasty, often being made with toxic heavy metals like lead or mercury stuck to weird ions like fulminates or azides, which are also kind of poisonous. This is why they're usually packaged in such small quantities. In the event an accident did occur with one, you might lose a few fingers, but you're not going to bring down the roof. In addition to all the issues with toxicity and volatility, primaries or any other sort of chemical initiation is unsuitable for a nuclear weapon. This is because a typical fission weapon relies on a series of charges uniformly placed around a plutonium core known as a pit that all have to go off within microseconds of each other in order for the shockwaves to interact to form what's known as an explosive lens and compress the plutonium above criticality. If one charge goes off too late, it'll basically be a low pressure zone that the plutonium sphere will just be ejected out of instead of being compressed in place. To give you some idea of the timescales involved, let's look at an example fission weapon like the Trinity test. What we've got is a sphere that's around a meter or two in diameter. We'll just call it a meter to keep it simple. To compress the pit, the weapon uses charges of melt-cast compounds like RDX or HMX, which have extremely high detonation velocities in the range of 8 to 9,000 meters per second. This means a shockwave would travel across the diameter of our example device in roughly 100 microseconds or a tenth of a millisecond. So if, for example, you had a 1% tolerance on the location of the shockwave within the device at any given time, that means the charges would have to go off within 1 microsecond of each other, or a millionth of a second. Here's some examples from Teledyne that show general-purpose wire exploders having a standard deviation of 500 nanoseconds or half a millisecond, and high-precision exploders having a 35 nanosecond deviation. Something closer to the 35 nanosecond deviation devices would probably be used in a nuclear weapon. This is an impossible timing constraint for chemical primaries, which typically have delays anywhere from tens to hundreds of milliseconds from the time current is applied to the hot wire inside a blasting cap. The good news is that achieving this kind of timing with an electric circuit is relatively easy, so instead of chemical blasting caps, exploding wire initiators are used to start nuclear devices. When you push current through a piece of heater wire like nichrome, it gets red hot, melts, opens the circuit, and then that's about it. With an exploding wire, a high voltage capacitor bank dumps its energy through a short length of hair-thin wire so fast that all the electrostatic energy converts to heat before the wire has a chance to break and open the circuit like the hot wire does. This results in the wire vaporizing into a hot plasma. But remember, this has happened so fast that the bits of the wire haven't even had time to blow apart, so they're all still mostly in the same place that they started in. Now, even though the wire has been vaporized, the plasma is conductive, so current keeps flowing and further heating the plasma until the capacitors are completely discharged, or at least mostly discharged, because you'll usually have some voltage left behind. By adding this much heat to such a small area in such a short time, a region of extremely high pressure is created that wants to expand outward. But remember, the maximum speed of the expansion is limited by the speed of sound of the air. This causes a shockwave to form as the pressure from the vaporized wire plasma pushes outward, which is functionally the same as a detonation, but without a chemical reaction. And thus, the exploding wire accomplishes the same function as the chemical blasting cap, with the obvious advantage being the ability to precisely control timing. The other obvious advantage is the safety of the device. As long as the capacitors are discharged, the device is completely inert, and of course there's nothing toxic about it. Now of course there are some design constraints when building one of these things. Simply hooking up a thin wire to a battery isn't going to cut it. Suppose you wanted to mimic the effect of 1 gram of TNT with a capacitor discharge. That requires approximately 4 kilojoules of stored energy in the capacitor bank. Now let's say we want all that energy to be released in under 10 microseconds, just as an example. We'll set our desired RC time constant, or the resistance times capacitance, to 10 to the minus 5. This is the time that it takes a capacitor to discharge 63% of its charge, which is 1 minus 1 over E. Then we'll say our bridge wire has a resistance of 100 milliohms, or a tenth of an ohm. That means our capacitor is going to need to have 100 microfarads to meet our RC time constant goal. In order for a 100 microfarad capacitor to store 4 kilojoules, the voltage has to be just under 9,000 volts. So obviously a battery isn't going to work for this. We also need to be extremely mindful to ensure the impedance of the capacitor bank and the transmission lines is as low as possible. That means making sure the parasitic inductance of the capacitor and lines is minimized. Because of this, film capacitors are typically used for this application, and the transmission lines are usually coax, like you can see in this example picture of the Trinity test device. The reason this matters is because even if we have a really small RC time constant, any inductance in the circuit can reduce the speed of the current rise time as shown by this formula. An example I found on Wikipedia gives a figure of at least 100 amps per microsecond of current rise time needed for a reliable wire detonation, which appears to be sourced from this book here. In this example simulation, you can see the difference in current rise times with 1, 5, and 20 microhenries of parasitic inductance in the circuit. It's very easy to unintentionally get this much parasitic impedance in the circuit, especially if the power leads going to the exploding wire are very long and or spaced relatively far apart. Having long, widely spaced leads effectively does the same thing as making a coil of wire and causes a lot of unwanted inductance, which is why coax with minimal length is ideal. Okay, that's enough theory. Let's try actually building something to demonstrate these concepts. I had a bunch of these fat electrolytic capacitors sitting around, so I'll start with them. This is a 3.3 millifarad cap rated for 35 volts, and I'm going to have 14 of them in parallel for a total capacitance of 46 millifarads. These will charge up to 30 volts through my benchtop power supply and discharge through this simple toggle switch. The total energy held in the capacitors will be about 21 joules. Our first victim will be some 36 gauge nichrome wire. And that was pretty weak. There was still about 28 volts left behind on the capacitor bank, so only about 2.6 joules actually went into the wire. This is an example of what I described earlier, where a slow hot wire will just melt, break in half, and open the circuit, preventing further heating. Now let's try 36 gauge copper. It's definitely a lot more snappy, but nothing earth-shattering. Okay, there was definitely a lot more energy transfer through the 32 gauge copper, probably owing to the larger mass and smaller RC time constant. This is about 16 joules transferred to the wire. Let's see the effect of reducing the RC time constant but keeping the same energy. I'm going to rewire the capacitor so that there's 2 pairs of 7 in series, giving a maximum voltage rating of 245 volts and a total capacitance of 0.94 millifarads. This will result in a factor of 50 reduction in the RC time constant, but at 210 volts, it'll have the exact same energy storage as it had before. Now, I should point out that capacitors, especially electrolytic ones, have some internal resistance and inductance. So in reality, they'd look like this. When you put them in parallel, you're dividing that series resistance and inductance by the number of capacitors. But when you put them in series, you're multiplying that series resistance and inductance by the number of capacitors. This is something to keep in mind when trying to design for ultra-fast discharges, because in the case of electrolytic caps, the limiting factor on discharge speed is probably going to be the parasitic elements of the capacitors themselves rather than the load or the transmission line. So anyway, the cap bank is charged to 210 volts with this simple rectifier doubler circuit that uses 2 diodes and a capacitor to turn 120 volts AC into up to 340 volts DC. Let's try that 32 gauge copper wire test again, but at 210 volts. It's hard to tell from the video, but that was a dramatically louder and brighter discharge, and it left a little smoke behind too. But it was pretty much the same amount of energy as before, using only around 15 joules going into the wire, so reducing the discharge time really makes a big difference. The higher voltage discharge also seems to have welded the contacts on the toggle switch, so we're going to need semiconductors for the next experiment. In this case, it's going to be a thing called a thyristor or silicon-controlled rectifier. At the semiconductor level, an SCR is basically a huge PNP transistor with an additional N channel. This allows the whole thing to be turned on with a single momentary pulse to the gate, at which point it's latched in the on state and continues conducting in the forward direction until current goes below a certain cutoff point, which is usually close to 0 amps. These things can handle massive amounts of current for a short time and do it at relatively high voltages, so they're good options for exploding wire circuits. The alternative would be a spark gap, which would cause a lot of energy loss. To charge the capacitors to higher voltages, I'm going to use a self-oscillating circuit called a ZVS driver that'll take 24 volts DC in and create a high-frequency alternating current for a small transformer that'll output 400 volts AC. The output is current limited with a small value capacitor in series and converted to DC with diodes so that it can charge the capacitors. The reason for the current limiting is because the ZVS driver can have trouble starting up if there's too much load on the output, and a large discharged capacitor is basically the same thing as a short circuit, so there has to be something to limit the output. For the next couple experiments, I'm going to use this 2.2 millifarad capacitor rated for 400 volts, which should carry a total energy of 176 joules. Just as a side note, never forget to add bleed resistors to a big capacitor bank, so if the circuit is left alone for several minutes, it'll discharge itself to 0 volts and be safe to handle later. The ZVS driver is connected to 24 volts, and like magic, the capacitor voltage starts to climb. After a few seconds, we're up to 400 volts. The first sample wire is 36 gauge nichrome at 400 volts. As you can see, the discharge isn't very exciting, and there's barely any mark left behind on the paper on account of the slow heating. Now let's compare that to 36 gauge copper. The copper left behind smoke, soot, and a bang that was incredibly loud even with hearing protection on. Wait, before we continue, riddle me this. Phones, computers, self-driving cars, AI girlfriends, airplanes, and your refrigerator. What do these things have in common, besides being cheaply built to maximize profit margin? Software, that's what. You may have noticed software is everywhere in your daily life, and it's going to stay that way until a random solar flare cooks all the semiconductors on Earth. If you're working in any space that's even slightly technical, you're probably going to run into a situation that calls for at least some sort of software, even if it's just a couple lines of code in a microcontroller. And that means you should be prepared by learning to code. Now, I know that's basically the most cliche phrase on the internet, but it's kind of true. Now, more than half of you are either Zoomers or Millennials like me, so you probably learn best from having a subject matter presented like it's World of Warcraft and not like a lecture in a 19th century boarding school. Well, guess what? Boot.dev does exactly that, offering interactive tutorials for Python, JavaScript, Git, SQL, Go, and several other programming languages structured like a role-playing game with experience and achievements so that every time you learn something new, your brain gives you that little dopamine hit you're so addicted to, which keeps you motivated to keep learning. Boot.dev is set up to actually get you writing code, which is by far the best way to learn instead of just watching or reading tutorials. If you're a competitive type of person, you can compare your learning progress against the global leaderboard, and if you ever get stuck, they've got this nifty AI teddy bear thing to help you out with your programming questions. They offer a 30-day, no questions asked, money-back guarantee, so if you try it and you feel like it's just not for you, you're not going to lose any money. Go to boot.dev and use promo code HyperspacePirate to get 25% off your entire first year if you choose the annual plan. Okay, back to whatever I was blowing up. And here's 32 gauge copper. This gave the best result by far, giving the brightest and loudest flash and leaving the biggest impression on the paper. Looking closely at the paper under the light, you can actually see the spray of copper that deposited itself on the paper, looking kind of like brownish-orange glitter. Okay, so now that we know that the charging and discharging circuit designs work, let's move on to the main event. The capacitor bank will consist of 5 10,000 microfarad caps rated at 400 volts placed in series, making the bank 2,000 microfarads at 2,000 volts, which will hold 4,000 joules of energy. The caps will be held in place with 2 3D printed brackets, and the series connections between them will be made with aluminum L channel. The negative and positive electrodes will be connected to 8 gauge leads with copper lugs for discharging and some small 20 gauge wires for charging. And of course I gotta modify the transformer a little bit in order to output the appropriate voltage. To verify I was putting out the right voltage, I made a 10-to-1 capacitor voltage divider and yet another 10-to-1 resistor divider on the bottom capacitor. This gives a total voltage division ratio of 110-to-1. When I fire up the ZVS driver, the output on the oscilloscope shows 20.8 volts peak, so multiplying that by the divider ratio gives 2300 volts. perfect. We want the output voltage to be a little bit higher than the target voltage of the cap bank, otherwise it'll basically flatline as it approaches the target voltage. Looks like a pretty good output arc. This is with 500 picofarads of capacitance for current limiting. This is the resistor bank for safe discharging. This totals out to 3 kiloohms with 6 resistor pairs in series, so there shouldn't be a problem with high voltage breakdown. The transformer gets boxed up in a case, the resistors get boxed up, and the rectifier is mounted to this funny 3D printed bracket. The reason I did this is because at 2000 volts, there was actually a little bit of current getting through the perf board due to close spacing of the plated holes. These 4 resistors here are bleed resistors measuring 100 kiloohms each. These will slowly discharge the bank if it has to be left unattended for some reason. This is the reverse protection diode, also known as a flyback diode, which is actually 2 diodes in series because they're individually rated for only 1200 volts, but I happen to have them on hand already. The diode is wired in reverse between the positive and negative terminals of the capacitor stack and also given its own case. This is the gate pulse transformer which isolates the SCR gate. Technically it's not necessary, but I was really paranoid about getting zapped through the gate in the event the SCR failed, so instead of directly connecting to a button, a short pulse is fed into it through the transformer. On the button side, there's a capacitor that basically limits the amount of time current can flow through the button because it's really not meant to take more than an amp or so, but the SCR only needs to pulse for a few microseconds, so I can push way more than an amp as long as I have that cap to limit the pulse time. This is the waveform of the pulse on the output side of the transformer across a 10 ohm resistor, peaking at 21 volts after 12 microseconds, meaning over 2 amps. This box houses the charging and trigger switches. That's the capacitor in the corner. The trigger switch is guarded to avoid accidental discharge. These lugs are put in place to clip the multimeter to. The positive lug is connected to the last of 4 bleed resistors in series, so it reads exactly 1/4 of the cap bank's total voltage, since it won't go to 2000 without blowing up. I 3D printed this little switch for connecting to the safe discharge resistors because I didn't want a switch with any metal on the body if I was handling 2000 volts. Also, this SCR may look big, but it's not going to cut it for this project. The datasheet says it can take about 1800 amps for 8 milliseconds, but if my math is right, the discharge current of my system will be between 10 and 20,000 amps, so we're going to need a bigger unit. This one claims to handle 14,000 amps for an 8 millisecond pulse. I may very well exceed that, but I'm willing to take my chances with it. I've 3D printed a shroud for it so I don't accidentally touch the terminals, then I went ahead and did the same thing for the capacitor bank itself. Probably the only component that's not covered in a shroud or case is the ZVS driver because it's one of the only parts on this circuit that doesn't have dangerous high voltage on it. And lest I forget, the actual energy source for this entire contraption, a 6-cell LiPo battery which slides into this little square tube. And that's the full assembly ready to cause some mischief. Now to test it out, I'm going to start slow because 4000 joules is a scary amount of energy. So for the first test we'll be at 800 volts, which equates to 640 joules. That probably didn't sound very exciting to you, but I can guarantee that the audio recording doesn't do it justice. That was extremely loud, even with hearing protection, and I could feel the pressure wave from a few feet away. And that's just 16% of the maximum energy. For the next test, I'll try 1200 volts, which is 1400 joules. I had to move outside because even the 800 volt test was way too loud inside a garage. An interesting detail here is that all the debris on the paper isn't from the wire, but from the pressure knocking loose wood fibers off the nearby fence boards. The multimeter reads 32.8 after the discharge, meaning the cap bank is at 131 volts. That means over 99% of the initial energy was used in the discharge, compared to the 70 to 80% used in the earlier experiments at 400 volts. Next we have 1600 volts, or just under 2600 joules of energy. Here's the impressions on paper comparing the different voltages. Each shot vaporizes approximately the same mass of copper, but the higher energies seem to spread it a lot further. The impression marks seem to be composed of copper particles at the center, surrounded by either copper oxides or burnt paper further out, and then this yellow layer which I suspect is some sort of nitration due to the nitrogen oxides that are formed at the super high temperatures of the discharge. Here's a side-by-side comparison between 2600 joules versus just over 100 joules from the earlier experiment. Next, I went to test the system at the full 2000 volts, but only managed to get a little over 110 volts on the bank. At first I thought this was a failure of the charging circuit, but when the wire was broken, it started pumping up the voltage with no problem, so it seems like I broke the SCR. I removed the SCR and opened it up, and it doesn't show any signs of damage, but once the voltage gets above around 100 or so, the junction breaks down and starts conducting. Despite the 14,000 amp rating, I still managed to break the thing. That was an expensive failure. I guess that means we're doing this the dirty way with a big mechanical switch. So I soldered the terminal lugs to some big copper blocks and sketched up a design for a heavy-duty switch to discharge the current. I guess in the future I could change this to a solenoid-controlled contactor and effectively make it a giant relay, but a hand switch will work for now. So here's how that looks. Not exactly elegant, but it should get the job done, at least for the duration of this project. I've got another wire strung up, so let's see how the switch handles those tens of thousands of amps. Seemed to work pretty well. There wasn't a huge arc on the switch, so I don't think there was much energy loss across it, but for some reason I blew up my flyback diode, and it's a good thing I was wearing safety glasses, because the top of the diode enclosure flew right into my face. As you can see from the paper impression left by the wire, very little of the energy actually went into the wire itself, and most of it went into blowing up the diode. Rather than spending a bunch of time trying to investigate and troubleshoot, I just removed it altogether. I don't think I'll really need reverse voltage protection because the total inductance of the load relative to the resistance is pretty negligible, and it might not even allow for a reverse voltage spike to occur. Firing again at 1600 volts, it looked like it left as big of an impression on the paper as with the SCR triggered circuit, if not slightly bigger. So the circuit definitely isn't losing any more energy across the mechanical switch than it was across the SCR. And finally, here's the full 2000 volt shot with 4000 joules of energy. This left the biggest paper impression, as you might expect. Let's see what the exploding wire can do when it's frozen into the middle of an ice block. I'm going to freeze two test samples, one with a copper wire and one with a nichrome wire, both of which are 32 gauge. Let's start with the copper. There were about 350 volts left behind, so 93% of the stored energy was consumed. Now let's try the nichrome. Standing right next to it, the nichrome explosion seemed to be just as powerful as the copper, if not more so, but there was still 800 volts left behind in the cap bank, meaning it only used 84% of its energy. Let's see what the exploding wire can do when it's confined inside some plastic bottles. This is an empty bottle, a water bottle, and a bottle full of ice. All three have about 2 centimeters of 32 gauge copper wire inside them. Let's try the frozen one first. The cap bank discharged most of its energy, but all it seemed to do was leave a black mark and a crack in the bottle. Next up, we have the water bottle. That's the kind of result I was really hoping for. I got soaked, but it was worth it. Here's what's left of the bottle. The water did a great job turning the heat from the discharge into pressure. Now let's try the bottle full of air. Surprisingly, there was no damage to the bottle itself, but it blew off the cap and launched itself forward. I think this might have some potential for a small potato cannon or something like that. Let's see if I can cut this rock. I guess not. All that did was leave a line of copper particles on the pebble. Maybe if I place this water bag on top to focus the pressure downward, it'll cut it. No luck with that either, but for whatever reason, having the water bag on top made the explosion way louder. On the subject of noise, at 2000 volts, the discharge from this thing is louder than shooting a 308, so I've had to move my tests out of the neighborhood and into an empty industrial area. Good hearing protection is mandatory for this much energy. Let's try some different wire setups. This is 2 strands of 32 gauge. And now a single strand of 28 gauge. And 2 strands of 28 gauge. Let's see that in slow motion. The triple 28 gauge blast left quite an impression on the paper, definitely the most smoke and brightest flash I've gotten so far. How about another empty bottle, this time in slow motion? The bottle cap traveled a ways off, but the bottle itself is once again intact. Definitely potato cannon material. Let's try some thin strips of aluminum foil. The aluminum was dramatically louder, and as we'll see from the slow motion footage, this seems to be because it's igniting in the air, adding to the energy of the blast. There's absolutely no aluminum metal left, just this bluish-white aluminum oxide. How about magnesium? That definitely worked, and the flash was much brighter. The smoke smelled exactly like a typical firework. Now for some produce. The fruits can be a bit hit or miss because sometimes they just generate a puff of steam instead of exploding depending on the electrode placement. It took 4 attempts to get a proper explosion out of this watermelon. Let's try a couple more experiments with the explosions underwater. I still don't understand why the bucket flies up instead of being pushed down, but it sure looks cool. I found that I can get a really dramatic effect with strips of aluminum foil buried in the dirt. Since they're spread out over a large area, the strips move a lot more dirt compared to just using a thin wire. Finally, here's some pencil graphite. At normal speed, it's really boring, but when we slow the video down, we can see a nice fireball as the carbon burns in the air. Looks like I'm attracting some unwanted attention in this particular spot, so I guess I'm not coming back here again. Anyway, that's my exploding wire machine. Thanks for watching.